Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Maude Gull with us today. Hello, Maude.
Hi, Frank. Thanks for having me.
Well, thank you for agreeing to talk about your very awesome article, which we'll get to real shortly. And let's see, it is July 29th of 2025 as we record this, and it's somewhere in the Northern Hemisphere. And do you happen to be in the Northern Hemisphere there, Maude?
Yeah, I'm in the Chicago area, so
Chicago.
enjoying the summer.
Yeah, yeah, Chicago's got a very interesting summer.
Yeah, it's very hot. Definitely very
And
hot.
humid. Generally
Yes.
humid comes with it, right? Yeah, so I lived in Chicago for about a decade. So yeah, I'm quite familiar with the weather patterns. So very cool.
Yeah. I heard in the Arizona area it was getting really, really hot the other day as well.
Yeah, we hit the 110Fs real quickly, about 38, 39 C.
Yeah.
And so yeah, we're pretty and we're going to be a little warmer today. So yeah, we're doing our usual summer thing. It gets hot. It's also the wet season in Phoenix. I don't think most people know that, but that's when the humidity
Oh,
is up a little bit and we get our various weather phenomena like monsoons and other things like that. So yeah, it's
oh.
the humidity goes up in the summer a little bit, but it's still a dry heat. We tell them it's a dry heat. Never notice it.
Yeah.
Very cool. And Maud, what do you like to do for research?
Yeah, so broadly speaking, I'm interested in metal poor massive stars. So these are stars at least 8 times as heavy as our sun, and that have a chemical composition, I would say, below about 10% solar metallicity.
Cool. Very nice. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. A low metallicity, massive contact binary star system candidate in WLM, identified by Hubble and James Webb Space Telescope imaging. And Maud, take us away.
Yeah, thanks, Frank. I first want to point out a couple of my co-authors on this paper here. Kareem El-Badri, who kind of really showed me the ropes as I got into this slightly new analysis method for me and introduced me to Phoebe, the modeling tool I'll be talking about later.
Cool.
I also want to shout out Jan Henneko, I guess, finished his PhD this year at Heidelberg and is going to be a postdoc. And he was kind enough to run a Mesa model grid for me. And
Yeah.
then Alessandro and Meredith are both postdocs at Berkeley who really also showed me how to do a lot of the data reduction
Nice.
that went into this paper.
Nice.
And everyone else can kind of lump into the Lubit collaboration. I've been working with throughout my PhD, and it's a bunch of really awesome scientists.
Indeed, it's quite the international collaboration there on this one.
Yeah.
So very nice. Very nice. Okay, let's go ahead and get into it on the introduction.
Yeah, so as I mentioned before, in general, I concern myself with metal poor massive stars. And something we've realized over the past 2 decades or so is really that these massive stars actually prefer to be in binaries.
Yes.
For some of the more massive stars, nearly 100% are expected to be in binaries.
Hmm.
And so we kind of, with that in mind, thought a little bit about, well, what about metal poor massive stars?
Yeah.
Um, the thing is, although they're kind of really important stars because they, provide most of the light of star-forming galaxies at higher redshift, they may be potentially, when they are in binaries, be the progenitors to gravitational wave sources.
Ooh. Okay.
Um, and so the challenge here is, though, that they're kind of rare. Massive stars in general are rare already in our local group, but
Hmm.
then on top of that, the really metal poor ones tend to be at large distances. So the closest galaxies are DOA or WLM um, at maybe 700 kiloparsec. And so even your brightest stars there are going to be just challenging to observe due to the distances, making them quite faint.
Yes.
I should point out at this point also that the SMC is much closer, and in the Magellanic Bridge, they found some low metallicity stars as well. However, again, we're in a like small numbers regime, or in the SMC, we're at slightly higher metallicity. But if we want to probe this really sub SMC metallicity environment, we kind of have to push out to almost a megaparsec.
Yeah. Okay.
Um,
I'm with you.
And so WLM is one of the closer by dwarf galaxies with about 15% solar metallicity.
Mhm.
And again, when I say close by, it's about, I think, 960, 70 kiloparsec away. So,
Relative,
you
relative.
know, depends who you ask how far that is, if that's close or far. And really, this project started because I was trying to find binaries. And so, as I explained, it's really hard to observe them. So, coming in and asking for, X amount of orbits to survey, to do a time series survey of a galaxy, um, is like challenging to convince someone if you don't have a proof of concept.
Right.
And so what I realized is that other people have studied other types of variables. So you can have RR Lyris, Cepheids studies in these galaxies for which time series photometry already existed.
Yes.
And so it's going into that type of sample that we found this candidate. And so if
Cool.
you scroll down a little bit to figure one,
Okay. Oh,
which,
there's our photometry, our imaging, and figure one. There
yeah,
we go. Optical ground. Okay.
yeah. So the image itself is I think, ground-based image of WLM from NORLab. And then what I overplotted is just the various footprints of the data we used in this paper. The HST ACS filter of photometry comes from said our Lyra study that my advisor, I think, headed back in 2015, maybe.
Okay.
Um, and really lucky for me, the same patch was also reobserved with Luvit. And so we have the UV bands
Mhm.
for that same star, which is
Okay.
indicated here in pink. And
Mhm.
lastly, it was also reobserved with really deep photometry as part of the early release science program that also my advisor, Dan Weiss, PI,
Mhm.
and a lot of people in our collaborations have worked with that data and done some really awesome science.
Cool. I'm with you.
And so
Mhm.
if we scroll down a little bit to figure two, we can see the star now plotted in this data as a point in the CMD.
All right, let's get there. And here we go. CMDs, HST and JWST. Bonk. Okay.
And so so to the left, we have the UV CMD with F275.
Hmm.
We have an optical CMD in the middle and an IR CMD to the right.
Yes.
And we overplot the various mass tracks to kind of just illustrate that at least one of the two components has to be somewhat massive since it's
Okay.
sitting quite high here on the mass tracks.
Got it. And so would this mass be the total mass of the binary or the primary?
I would say the primary.
Okay. Okay.
Um,
Mhm.
so what all we're saying is that at least the primary has to most likely be above 8 solar masses, so be a massive star. The
Yeah.
secondary might or might not be one.
Okay.
The other thing that we point out here is, if you didn't know this was an eclipsing binary, based on the CMD, there isn't really anything that tells you, oh, this is a weird system, right? This looks almost like a perfectly standard single star sitting here on the mass tracks.
Yes.
Um,
Uh-huh.
and so when we scroll to figure three is when
Okay.
it's being revealed to us that actually this is an eclipsing binary.
Aha. Look at this. Okay.
And so again, to the left here, we have the optical, which came from this RLIRIS study, which they covered this part of the galaxies for 3 days. And
Cool.
so you can see the unfolded data here. And obviously there's some gaps in between when no observations were being taken, but you
Hmm.
can clearly see kind of this traditional bow archy um, signature in the light curve, which is typical of closed short period binaries.
Yes, I'm with you.
In the UV, we were a little bit less, I wouldn't say less lucky. We're really lucky to have UV points for this in the first
Yeah, we got
place.
two. We got two.
But in total, there were four exposures.
Okay.
However, three out of the four showed some flags in our reduction. So we really only felt comfortable with those two data points.
Okay.
And then nicely, again, here to the right, the IR. And
Yes.
so what's really cool about this is, as I was talking to you about the JWST data, it's not a time series data. It is really deep photometry. So what does that mean?
Yes.
They looked at the same patch for a really long time, I think about 13 hours. But when you're looking at bright stars like I am, bright, sorry, for this sample,
Understood.
um, you can actually just look at the individual exposures and treat those as kind of your data points. And so this
Yeah.
is actually really just back-to-back exposures of that same patch. And again, it gives us a really nice dip here
Yes.
from the eclipse and a little bit of continuum in the reddest filter.
Very cool. Okay.
And so now you kind of move to how do you analyze all of this data really quantitatively, right? All of this was a very nice qualitative description. And so that's when we turn to Phoebe. Phoebe is a really great binary modeling tool. Um, However, for my purposes, there was one little problem, and that's generating a Phoebe model can take up to a minute. So if you want to do some, statistical fitting, that
Right.
can really slow down your process.
Right.
Which is why I decided to build an emulator for Phoebe for my binary so that I could sample more quickly and so be
Okay.
able to derive some robust uncertainties on my star.
Very
And
cool.
so table two kind of describes the model grid that we created. And
Huh.
so kind of agnostic of whether this was a contact or not contact binary system,
Right.
we created two grids, one for the contact system, one for the detached system, as they have slightly different kind of prescriptions on how the light curves are treated.
Yes. Okay.
And you'll notice it is a little bit tailored towards this object. Kind of the period is quite tight, which we determined from previously from a periodogram.
Hmm.
Um, and also we're making some assumptions that it is most likely a hot star based on what we've seen in the CMD, right? If it had a much cooler companion, we kind of would have expected it to potentially shift across the main sequence a little bit more than what it did.
Cool.
Um,
I'm with you.
and so when we go to figure four, that's kind of just an overview on how different parameters affect the life curve. And I will point out here that this is really just for one band. So it's not capturing all the effects that we can capture or measure with multi-wavelength photometry. So for example, um, dust, so AV here at the bottom right, is not going to affect each filter band exactly the same way. We know it's going to
Yes.
push down the UV if there's more extinction, but push up that, or sorry, not affect the IR as much. Um, and so there's actually additional information by having all these various filters on hand as well.
Nice. Okay.
The
Hmm.
other thing I would like to point out is the mass ratio at the top right here. And that is a parameter that traditionally has been really, really hard to disentangle from the photometry alone.
Okay.
And this will also, I think, come back to why we describe the star as a candidate, because you can see that the differences are really, really small. And
Tight.
although we have quite high precision photometry,
Hmm.
uh, it is still kind of, I guess, the most uncertain parameter.
Okay.
And so,
Also the most important. So,
yeah. Um, and so I kind of first actually attempted to solve this by just, plugging it into MCMC.
okay.
But what you will find out is that it doesn't really converge. And that's why, or it doesn't converge really fast, I would say. Um,
Fair. Hmm.
like I read it for like 3, 4 weeks and it wasn't converging. So
Yikes.
um, we needed to find something else. And the main reason this was happening is actually because the period is multimodal. So it has a very high likelihood when you're on like in phase. And then if you shift slightly off that, the probability will almost drop to zero. But
Okay.
then again, very close by, the next kind of in phase period gives you a quite high probability. And so
Right.
what happens if you just naively use MCMC, you're going to hop from kind of peak distribution to peak distribution.
Right.
And so that can kind of go on forever. And
Right.
so
Never.
um,
Yep.
in statistics, they've been exploring, and I think other physics fields as well, kind of this nested sampling that does a slightly better job at exploring also multimodal distributions. And so if you look at the corner plot, which is figure 5,
Figure
you can really see what I'm talking about here in the periods.
Ultranest. Okay, let's see. Here's our corner plot. And there we go. Let's zoom out a little bit. Okay, we got it all.
Okay. So
Ultranest.
you can see the period, which is, I think, the sixth
Yes.
column.
Yes.
You can
Ooh.
see those kind of drops, and they have really high probabilities right in the middle, and then really, nothing, and then really again a high probability
Right. You that
set.
double peak structure. Yeah, yeah. Uh-huh.
And so I think the other thing to point out here is, let's see, do we have?
Well, that would make sense.
Oh, where am I seeing?
Okay.
Um, yeah, we have mass ratio is another one that's just sorry, not multimodal, but just like pretty wide distribution, which is
Right.
what I was talking about earlier, that those small differences can be really quite hard to disentangle. And the last one is the fill out factor. So this would be right next to the period.
Right.
And so the fill out factor really measures how much are your two binaries in contact? So
Oh,
are
okay.
they both, to what degree are they both overfilling at their Roche
Okay.
potential?
And so just to get the scale here, 0 would be no contact whatsoever.
Correct.
I'm with you. Hmm.
And so, yeah, from seeing here, you might ask, okay, it's really low. Is it maybe not in contact? And so that's a fair question to ask, which is why we also ran the detached model.
Okay.
And so what we find there is that in the detached model, one of the system does overflow certainly,
Okay.
meaning it would be considered semi-detached.
Yes.
And the second one is right at the limit to overflowing as well.
Okay.
And so
Interesting.
statistically speaking, we didn't really find a preference towards either. Like their evidence are really close to each other. And so this is why we said, okay, this is a candidate. It's a contact binary system candidate.
Yes. Yes. Yes.
Um,
Okay.
and so table 3 kind of summarizes those parameters.
Okay.
We also derive a couple of parameters from what we fitted. So we have temperature of the secondary, mass of the secondary,
Yes.
their separation. And using Phoebe, we can then also determine radius, surface gravity,
Right.
um, and so on. And so what we see is, as we kind of anticipated, the primary does appear to be a 16 solar mass star,
Uh-huh.
which would be a massive star. It's
Mhm.
quite hot, around 30 kilocalvin.
Yes.
And looking at the secondary, it's a slightly less massive star with 7 solar masses, though the uncertainties are a little bit larger. So
Yes.
maybe it could be 2 massive stars. Um, it's just generally a little bit cooler. Um, and yeah.
Yeah, it's certainly within range. It's right at the border there at 7, plus or minus,
Yeah.
plus 5 minus 3. So yes, could be.
And also this is, I would say this is present day mass.
Yes,
We don't know what their initial masses were for sure.
that's for sure. Okay.
And so I'm before talking a little bit more about those results, I'm just going to show kind of what the fit to the data actually looks like.
Okay.
And so that would be figure 6.
Okay, let's slide on down. Okay, we're going to do some stellar evolution modeling here. And figure 6, and there we go. I'm going to zoom out to get all of this, but these are the multi-band light curves, yes.
Yeah, so compared to what I previously showed in terms of data points, those are face folded. So on the
Okay.
bottom axis, we have the phase
Mm-hmm.
versus the various magnitudes. And so the black line is,
Okay.
I believe, I need to remember if it's our median or our best fit. Or I don't say, I think it's probably our median.
Okay. Okay.
It
Yeah.
says it in the text. I just can't remember the top of my head right now.
Yeah.
And then the colored lines kind of showing the width to it,
Yeah.
those are random draws from the posterior. And so what you can see is obviously that first dip here in the middle on the optical.
Yes.
It's quite well constrained, right? The posterior draws are all quite tight.
Yeah.
As we go to the second dip, that's mostly going to drive the parameters of the secondary. You can see that
That's really tight.
it's a little bit more, it's a little wider because it's a little bit more uncertain since we don't have any data points there.
Okay. Yes.
And I also want to just like point out again that all of this data was fit simultaneously. So we're really taking in all of the information
Good.
at the same time.
Good. I'm with you. Mm-hmm.
And so if we go to the UV, that's where we have the least amount of data and unsurprisingly have the largest uncertainty. And so really, if you would want to perfectly kind of constrain this system really the best as you can photometrically alone, you'd probably want a couple more UV points
Okay.
to really, sell that shape.
We'll come back to that. Okay.
And so now, okay, great. We have a contact binary system, but can we do more? And so this is when I approached my friend Jan Hennico, who I knew is a really great contact binary modeler actually, and asked him to run a couple of grids for me to see if we would be able to match the observed parameters with a single instance in time in a MESA model that
Okay.
will kind of explain how the system came to be.
Mm-hmm.
And so, kind of table 4, figure 7. Table 4 summarizes a little bit the kind of grid we constructed.
Okay.
It is quite coarse in that sense. Like we didn't explore all the parameters just because that is computationally quite expensive. However, with some of the MESA grids that have been released recently by Poseidon, for example,
Yes.
one could do this a little bit more holistically. And to the right in figure 7 here is actually one of the models we found a good fit for. So the
Good.
black points
Yes.
are the points where we have our observations. So those are the ones that match with our observations.
I'm with
And
you.
then the colored lines, so in the top plot, that'd be orange and green. And then
Yes.
for the remaining plots, that'd be red and blue, are kind of the upper and lower limits
Okay.
from our observational data.
Okay. I'm with you.
And so, what it seemed to have happened in our system, right? This is hypothetical, could also have various other formation scenarios,
Sure.
is that the system was born quite close together and experienced a quite intense, can say, mass transfer
Okay.
early on
Okay.
a very short time scale.
Uh-huh.
In that time scale, it kind of flipped mass. and then separated a little bit. And
Okay.
over time, it started to get closer again. And so that's what, like, as the, I guess, stars expand, I think probably the one, two, three,
Yes.
fourth panel in that plot,
Uh-huh.
R over RL, which is radius over Rochelot radius,
I'm with you.
shows you that they're kind of a little bit far from filling their Rochelot for maybe 2 million years or so before
Yeah.
entering a prolonged semi-detached phase. So this is the phase I was talking about where only one star fills the Rochelot,
Uh-huh.
and the other star does not, before in the last million years or so
Okay.
um, being in contact. And so our star does sit like very close to that
Yes.
turnover, which probably makes sense given the data that we're seeing in terms of the fill-up factor being quite so low. And so we were certainly interesting to do a more extensive search and see what other kind of scenarios could potentially reproduce the observables we have.
Okay. Very cool. And let's see a little bit on this plot. So those gray bands are the region where it's semi-detached.
Correct.
Okay. And then in the pinky color there, that's if it's a contact
Yeah.
or when it's in contact. Okay. Okay. All right.
Um,
And
and so I would say out of the other, I think we found another maybe three models that matched our observables,
okay.
my, with the exception of maybe one. Of them. And in general, it was kind of a similar picture where they were all systems that had a prolonged semi-detached phase and then a contact phase.
Okay. Good. I think I'd rather have a multitude of models that do the trick than only one, given the state of the data. So yeah. Uh-huh. Good.
And yeah, and then I think something we explored, I'm just going to briefly touch on this
Sure.
in figure 8, is that something we found out about the low metallicity regime recently in the massive star community, but had been suspected for some while,
Okay.
is that the mass loss is lower at low metallicity, but actually even lower than what we thought it was.
Okay.
And so Vink 2001 is the Win subscription that's in standard use
Yes.
in Mesa. And so we compared that to the Björklund 2021 Win prescription that does slightly better at matching some of our observables in terms of mass loss rate.
You.
And in this plot, you can see that it doesn't seem to have a big difference between the two. But there's a bit of a caveat here I want to add, and that is we are not only in the low metallicity regime, but for massive stars, we're on the low mass end.
Yes.
And so these stars are in the weak wind regime just from their mass alone already.
Yes.
And so the low mass that they get from the Vink subscription in this case maybe just doesn't win out against the binary interaction. So I think for this particular system, the binary interaction just dominates the evolution. And so um, as long as your mass loss rate is pretty low, it's going to be okay.
Okay. Yes.
Um, the other thing we did is compare how different metallicities can affect this evolution.
Okay.
And so 14 here is the WLM evolution, and then we have 10 is the 10% solar is above, and then the like teal turquoise is 20% solar.
Uh-huh.
Um,
Okay. There's a progression. Yes. Uh-huh.
and I think this was just it was to showcase that mostly um, we could be a couple of percent off in our metallicity,
Sure.
but overall the picture is likely going to be the same, with the exception that in a higher metallicity environment, it seems like it takes the system a little bit longer to merge in comparison to
Yeah.
our low metallicity environments. And so I
Yes.
think this is also just more so to showcase that if we want to understand some of these binary products, it is actually really important to study them in different metallicity environments, as they may lead to slightly different results.
Cool. Good. I'm with you. Hmm.
And so I guess the last two plots we're going to talk about is first figure 9, which this one really shows you in really, I think this is all the contact
Yeah.
binary system and semi-detached systems
Wow.
at LMC and SMC
Kind of
and
distant.
sub-SMC metallicity. At
Okay.
the time this paper was published. I
Okay.
think there may be a couple more coming out of the Bloom survey, which is this large binary survey of the SMC.
Yes.
Um, but this is kind of what we had at the time. And so anything that's kind of blue shaded or purple shaded will be LMC, so
Okay.
large Magellanic Cloud. And then the pink ones will be SMC, small Magellanic Cloud. So this is,
Okay.
you go from about, I think, between 30 to 50% solar metallicity
Yes.
to 20% solar metallicity.
Uh-huh.
My system is here, the little black star, and in green, I included one Milky Way system,
Ooh,
which
yes. Here.
is
Yeah.
a system that's actually also really just minimally in contact. So it's one of the systems I found that was the most similar
Okay.
to our system, although it's quite a bit more massive.
Okay. Let's see. Find that green one here. Yes.
Yeah, it's right on that line. So I'll talk
Okay. Got
about the
twice.
second plot
Twice.
as well.
Uh-huh.
So in the two lines I draw here are really just kind of for reference and empirical. So the top one is just draws a line at I think about 1.2
Yes.
period, because for the most part, binaries that have shorter periods than that are likely to be in contact system if they're massive, just from a
Okay.
pure like mathematical like scaling relation.
Uh-huh.
But it depends obviously a little bit on the mass. So like there is two contact binary systems that are above that line, but those are really big systems. Like we're talking 50 solar masses.
Oh, yeah.
So they obviously can become quite larger and so
Uh-huh.
can be a slightly more distant and still reach contact.
Okay.
The line I drew in the bottom panel
Here.
goes through two, no, actually, I think three of these barely in contact systems.
Okay.
And I specifically just drew that because I wanted to see, does our star fall above or below that line? And it falls below, although some of the uncertainty could push it above. And so, um, in general, I would say it looks like the system tends to live where most of the contact systems tend to live. But that
Yeah.
might not be saying a lot, given that it's really just about 12 systems.
Uh-huh.
Um, and
Numbers.
so someone that isn't interested in massive stars says like, okay, why do you care about this mass ratio of the contact systems in the first place?
Okay. Yeah.
Um, and so actually when people model binaries, there's really different assumptions that go into their modeling. And
Yeah.
depending on which assumptions you make, you can get quite different distributions. So some people predict that all contact binaries should like pool towards this nearly equal mass end, which would be around 1,
Okay.
while others say no, you can definitely have contact binaries, across the board and find them in all kinds of mass ratio configurations.
Yes. Okay.
And so I think increasing the sample of contact binaries here will help us understand fundamental physics about binary interaction, mass transfer, and also in contact binary cases, actually energy transfer, which
Uh-huh.
are
Uh,
all physical phenomena that we're still a bit uncertain about at this point.
okay.
And
Right.
so projecting this forward, those kind of recipes are what go into, your stellar population modeling,
Cool.
your
Yeah.
gravitational source, like progenitor modeling. And so fixing that on our end could really also help those fields with their interpretation of their observational data.
Right. It ratchets up as you go through the fields. Yes, agreed. Okay.
And so now it's the kind of the question is, okay, how do you confirm this is a contact or not contact binary?
Okay.
And so that is actually quite challenging to do in general. But one thing that's missing from this system is spectra. And
Yes.
so why is spectra so important? There's a couple of things. So if you go to figure 10, you can see
Yeah.
probably the arguably
Yes.
most important aspect.
Instead of radial
Um,
velocity curves. Uh-huh.
correct. And so why do we care about radial velocity curves? Well, even for massive stars, this is actually the most accurate way for us to determine the masses of our system.
Uh-huh.
A lot of other ways we determine mass is very dependent on stellar atmosphere assumptions or other type of evolutionary assumptions. The
Yep.
dynamical mass is a very direct measurement that gives you, you know, your actual mass of your system. And
Cool.
so what I plotted here is also the difference in light curve that we expect based on whether it's a contact or semi-detached system.
I'm
And
right.
so the semi-detached system here is generated using the parameters we had for our best fitting semi-detached model.
Mm-hmm.
And so in that model, the mass of the secondary was actually slightly higher, which is why you see that the kind of primary suddenly has a slightly higher amplitude because the other star is slightly more massive,
Yes.
pulling on it a
Okay.
little bit more.
I'm with you. Mm-hmm.
And so, I mean, that's actually very new news. I have some already two observations of the system that we just took maybe a week or so ago. And we have two more coming up. And so we're really hoping to be able to constrain this radial velocity curve
Mm-hmm.
that will help us determine the true nature of this object, or
Cool.
sorry, of the system. And I think the last thing I will comment on, oh, I guess I didn't comment on the fact that also just seeing if we see any, signatures of interaction on in the spectra, or
Uh-huh.
um, if we are lucky to see both line profiles of the primary and the secondary, this will
Yeah.
also give us
Yeah.
additional constraints on the temperature of the systems.
Yes. Okay.
And so I think this is really, the first one of its kind to be published that way, but I don't think it's the last.
Yeah.
I think we're certainly first of all, there's some more that I found that I'm hoping to get out there, but also with LSST coming online, we'll definitely have more light curves um, out to even those far out local group dwarf galaxies. And I think also if we can get UX out there, that will be really neat for the massive stars, especially because they're so bright and strong in the UV.
Yeah.
Um, yeah,
Very cool.
but
Beautiful. Beautiful work. Maud, I want to thank you so much for walking us through your very awesome article. Very nice.
thanks.
Yeah. And you kind of touched on it a little bit there toward the end, and actually a little bit as we went on through. So let me go ahead and push on it a little bit more. And where do you think we go from here, given the published article in the somewhat short term? So you mentioned LSST, Ruben. Might other ones like Roman be of use? And what does it take to get, you mentioned that there's perhaps a couple of dozen of these potentially content. What does it take to get 120 of them? What do we need to jump that up by a factor of 10?
Ooh, that's a tough question. I think,
Yeah, and you don't have to answer it.
yeah.
I'm just throwing out ideas here.
I mean, I think there's kind of two ways to answer this question. First, what are limitations, right? And I think part of our limitations to get more of these systems is that you would really need to survey, galaxies again out to 1 megaparsec and beyond.
Okay.
And from the ground, this is very challenging to do. Like, I think LSST will do a great job providing, at least for the bright stars in those galaxies, some baseline.
Right.
But I am thinking they will probably need to be supplemented by some additional data. So I think discovering them with LSST and then following up with HST or JWST data will be probably the most reasonable thing to do. The other thing I will point out is actually, again, a little bit highlighting LSST here, is that we don't have a full census of all the massive binaries in the SMC necessarily yet.
Sure. Yeah. I'll do.
Um, and so that also includes some binaries that, come from massive stars, but might not be massive anymore at this point. I'm thinking something like strip star binaries, right? And so
Yep.
I think LSST and again UVEX in the future should really be able to give us a more complete sample, at least of the galaxy that is closest to us. Dwarf galaxy that's closest to us, which is the SMC. I think to get out there to the other ones, again, I think having a UV telescope, like I'm even thinking maybe HWO, like in the
For
future,
example, yeah,
thinking really far ahead in
yeah.
that sense. I think would really provide the detailed and high precision photometry we need for these massive stars that are unfortunately just a little bit further away than we would like for our optical telescopes.
Yeah. Yeah.
I think paired with that is like spectroscopic follow-up, because
Yes.
I think photometry does a great job giving you a sense of what the system is,
Yes.
but it is still quite heavily dependent on our models. And I think something we have seen in the massive star community at this low metallicity is that um, sometimes this regime can still surprise us. And so I think working closely with the modelers and theorists to kind of have this exchange as more data comes in will really push our field forward.
Very cool. Well, it'll be really fun to see this develop over the next couple of years, particularly as new facilities come on and you do, high signal don't always follow up on the spectra of these things. It'll be really cool to finally say something about what this particular system is, but also others. It'll be really fun to see this develop. I'm
Yeah.
predicting an awesome PhD thesis.
But I'm finishing up this summer, so
Okay.
yeah,
Well,
yeah,
congratulations, Dr. Gull. Let me say
yeah.
that.
I still have a couple
Yeah,
weeks left,
yeah,
so
yeah, yeah. Very good. Very good. That's awesome. Well, congratulations. Nice
thank
work.
you.
Nice work. Very good. And that will do, everyone. And I hope this made your contact binary astronomy day just a little bit better. And we will see you on the next one. Bye bye.